like 50 millihenry or 5 millihenry or whatever the value is. And if you take the same two terminals and simply change measurement from inductance to resistance, it will give you some value for resistance also. So it is physically part of that component. We cannot separate it out. Does that make sense? We cannot separate it out. But when we draw a circuit diagram, when we perform a mathematical analysis, we can model that resistance as being in series with an ideal inductor. Okay. So did you all use the orange, yellow decade boxes as inductors in the lab? Okay. Those are intentionally low quality inductors. We also have high quality inductors, but those are low quality inductors, which actually make it for very easy to do lab 6. So you have resistance R, and this is the, this is the inductance L, and that is the inductor resistance RL. And the ratio of L or RL is known as the Q factor or quality factor of that inductor. Okay, Q is used for several different notations, but in this case, that Q is describing the quality of that inductance. It's actually, sorry, it's not L over RL, it's L over XL. What am I saying? It's XL over RL. XL is the reactance of that inductor. Reactance, if you have not yet reached that point, you will review that in the lecture homework. XL is 2 pi FL, or simply omega L. So if it's an ideal inductor, RL is equal to 0, quality is infinite. Okay. So in lab 6, what you're doing is you're simply taking a AC voltage and applying it to this inductor. And we connect a resistor in series with that inductor to simulate a low quality inductor. But when I teach 251, I say we do not use the extra resistor. We simply take the inductors as itself, increase the inductance to like 50 millihenry, and you'll have a resistance of like 100 ohms, which causes a voltage drop, right? So if it causes a voltage drop, we can only measure this at the outer terminals. This voltage is measured. In the lab 6, it is known as VZ. But what portion of this voltage drops across the inductance and what portion drops across the resistance, we cannot determine it directly. We have to perform mathematical calculations, or we can do a graphical analysis. That is what we do in lab 6. We apply this voltage, and what we are doing is we are plotting this on the x-axis. So we have this plot. Our resistive portion would be here. So we are going to call this VRL, the voltage that drops across the resistive portion. Then the inductor voltage, inductor has an angle of plus 90 degrees. And so it points straight up. This is VL. And then we join it together, we get VS. Okay. This is nothing but KVL. We are applying KVL. KVL is source voltage must be equal to the inductor voltage plus VRL. Okay, these are vectors. These are complex numbers. Sorry, not vectors. They are complex numbers. Their complex quantity means they have a magnitude and they have an angle. So KVL still applies, except we are now adding magnitudes and the phase angles. But the only thing we can measure is the RMS quantity. So from that RMS quantity, we need to determine the phase angle as well as the length of that vector. And that's, again, that only is possible if we graphically draw it out. So that's what we did. Okay. But lab 6 is nothing but KVL. So if you already did lab 6, you're done with it. This is a little bit of explanation that would, that would help you understand what you actually did. All you're doing is you're doing KVL. You have a source, you applied it to an inductor, and then you balanced it out with a capacitor. Hold on. Lab 6, 7, and 8 are all based on the same concept. Okay, so lab 6, 7, 8, they're all related. So it's not as if you're done with lab 6, this is done. No, lab 6, you did the phasor diagram, you applied KVL. Lab 7, you're going to take capacitor, you're going to add it on there, you're going to measure the frequency response. And in lab 8, you're again doing the same thing, except you're now looking at the energy that is coming from the capacitor and the inductor. Okay. So again, if you have any questions about the lab or the lecture, just feel free to reach out. Okay. All right, let's end here today, and then we'll pick up here again on Friday.